Hi, and welcome to S for Science. And today we're going to learn how to make a nuclear bomb. And why a nuclear bomb? Well, even though it is one of the weapons which have taken the most lives throughout history, it is also one of the most powerful and useful tools that humans have ever created. Able to, for example, divert an asteroid that would crash against the Earth. It allows the construction of big projects like tunnels or canals, and it would also allow the terraforming of Mars, such as many other things. Let's start by analyzing the name, nuclear. This is because the energy released during the explosion comes from nuclear reactions. There are many reactions of this kind, but for these bombs we're just interested in the two that release the most energy. These are nuclear fusion and fission. Since we're children, whatever the reason is, we think that people at the centrals do nuclear fusion. Maybe it's because the name is more beautiful or seems more attractive, but that's wrong. Because we're in front of one of the most wrong ideas about nuclear energy. Because what the centrals and most of the atomic bombs have really been doing throughout all these years is to produce fission reactions, which is reactions in which atoms break. Let's begin then with nuclear fission. Fission comes from Latin and literally means to divide. And this is basically what they do to atoms. They take a mass with fissionable atoms and they activate it with a neutron bombarding, which produces the beginning of a series of chain reactions where the atoms get dividing into smaller ones, while releasing huge amounts of energy. To understand how nuclear fission works, think about this analogy. Imagine yourself in a supermarket and that you find a pile of oranges perfectly stacked up and in perfect balance, and then you grab another orange and throw it against the pile's base, which will produce an imbalance and would release much more energy than the one you had provided first with your throw. The same thing happens in fission. You had initially just one group of atoms, one pile of oranges that spills to the floor, the oranges fall, and a lot of atoms get formed, and also much more energy is released than the one you had provided to the system at the beginning. This is what happens in nuclear bombs and the nuclear centrals, where fission reactions are used. Now we need a way to get the pile of oranges. Each orange, according to our analogy, represents a group of protons and neutrons. So in this case, the pile of oranges would represent an atom. So we need really big atoms, as you can imagine. Let's remember now that in the periodic table, the elements are ordered by their atomic number, which refers to their quantity of protons. Therefore, the higher the atomic number is, the more protons, or metaphorical oranges, in one atom. And it's this atomic number what defines an element. Hydrogen will always have one proton on its nucleus. The only thing that could change is the quantity of neutrons. But we will talk about that later. You might think that the best way to get the biggest amount of oranges is using the last chemical element, the 118th. Well, yes, that would be theoretically the best. The problem is that the pile of oranges of this element would be extremely big, and therefore unstable. So using this element is impossible, because once created in the lab, it disintegrates in less than milliseconds. So all we have to do is look for a chemical element which doesn't disintegrate suddenly while having the highest atomic number possible. And the element that achieves these conditions is uranium. And that's why it's famous, not because people likes it more than its neighbors, like actinium or americium. It's because it's in the perfect place of the periodic table. It's the element with the highest atomic number that doesn't disintegrate fastly. Okay, so now we need to get uranium. Well, we can get it mainly from a mineral, which its name is quite original, uraninite. This mineral is a uranium oxide that can be found in several geological contexts, from igneous rocks to sedimentary rocks, being Kazakhstan the first producer. But practically at least a little of this metal can be found in any country. In fact, there is uranium even in the ocean, and in your body too. Now we have uranium. Now we have to enrich it. This is because of all the uranium atoms that exist, not all of them are the same. While all of them have the same number of protons, as we said before, that's what defines which element an atom belongs to, some of them have different numbers of neutrons. While they don't define the element of an atom, they do define some of the characteristics of them and makes them a little bit different. And this is called an isotope. Uranium has many of them, but in this case we only care about the 235th. So we have to separate them from the rest. Only this famous isotope the uranium-235 is unstable enough to produce a chain reaction. It is also called enriched uranium. To get it, they use separation methods such as centrifugation on the uranium gotten from the mines. And the uranium-235, the one we are interested in, is separated from the rest, as different isotopes have different densities. Alright, we have a way to produce it, and we have the orange pile. Now we just need the device, and honestly, it's extremely simple. We just need to put inside the enriched uranium at a conventional chemical explosive, like a firecracker, and connect it in a way so that most of the uranium is consumed before the bomb is destructed, and boom. And there you have the fission nuclear bomb, which is the bomb that you need to make the next type of nuclear bomb, the fusion nuclear bomb. Much less polluting, but much more powerful. Fusion comes from Latin and means to melt. And this is precisely what it's done in nuclear fusion. They grab two atoms and join them in one. This is what happens naturally in the stars, and it's the reason of this bomb's amazing power. Fusion is like fission, but the other way around. Instead of separating atoms, we merge them. And right now you may notice a little contradiction. If both with fusion and fission we get energy, couldn't we repeat the process infinitely with the same quantity of atoms and get infinite energy? Well, unfortunately no, because fusion only produces energy if elements with a lower atomic number than iron are used. And this happens because iron reaches the most energy possible of nuclear connection, which means that this is the last element in which after the fusion, more energy is released than the necessary to start it. In other words, it is the last element that, while fusing, releases more energy than the necessary to defeat the electromagnetic force that joins the atoms. Since before fusing, they need to beat the repulsion that the protons of the nucleus apply to each other, as they both have positive charge. This is the reason why elements with more than 26 protons, iron's atomic number, are produced only in supernovas, as they need colossal amounts of energy to fuse the atoms. To produce fusion, you just have to get a big number of atoms with the less atomic number possible because of the already mentioned energy connection and add a bit of energy. As we said before, this is because atoms repel each other at first, since having protons in their nucleus make them all positive. But if they receive enough temperature, the electromagnetic force can be defeated and the atoms fuse, releasing much more energy than the necessary to start their reaction. This produces, just like in nuclear fission, chain reactions, as more energy is released each time. An example of the time that these reactions last is the sun. It has been working for millions of years non-stop. Now you know how to do it, you're just missing the raw material. Remember, the lower the atomic number is, the better. So hydrogen and helium, the first two chemical elements, work for us. The good thing about these elements is that, contrary to uranium, they are much more common. For example, hydrogen is part of the water molecule. The problem is that even though hydrogen is really common, we need, like with uranium, a specific isotope. So not all hydrogen atoms are useful. Specifically, you need to separate deuterium, which represents a 0.02 of the whole hydrogen on Earth, a process that is really not that difficult. It's also necessary for the bomb to have lithium, the third element in the periodic table, to produce the explosion. Okay, we're getting close. Fuel and method. Now we're just missing the device. In this case, it is quite complicated, as we need a lot of energy to start the reaction. And what better than to use another nuclear bomb? Indeed, as we said before, fusion bombs are turned on by fission bombs, which start the reaction. So the fusion bomb is actually two bombs. The one that creates the spark and the one that provides the fuel. And then comes the boom, a much more powerful explosion than the one fission bombs produce. In fact, after antimatter, fusion or thermonuclear bombs is the method that produces the most energy per fuel unit. Here you can see a historical example, a comparison between a fission bomb, Hiroshima's, and a fusion bomb, which corresponds with the biggest explosion ever made by humans, the Russian Tsar bomb. There hasn't been a more powerful bomb, not because it is impossible, but because even the Russians thought that it was enough. Now, at this point, we know how to make a nuclear bomb, a weapon that has been used throughout history to end thousands of people's lives. But as we said at the beginning of the video, it doesn't have to be used for that. The power that this amazing invention provides is useful, for instance, for important scientific investigations, just like the comprehension of Earth's magnetosphere or the discovery of new elements, for big engineering projects, or maybe to one day make space trips shorter than what they are now. Maybe taking us to Mars in less than a month. Or maybe to save humanity in case of a meteorite crash. And all thanks to science, which gives us tools that as evolved beings that we call ourselves, we have learned to make. And that's not bad at all. But we still have to make one more step to learn how to use them correctly. Thank you very much for watching the video, and goodbye.